Strictly speaking, the power laws apply only to elementary reactions, or they are the simplest when applied to elementary reactions. What an elementary reaction is basically a reaction that only has one step. Um Most reactions do not happen straight away. So basically, we usually have the molecules, for example, stretching, breaking their bonds, and then forming an intermediate product in an intermediate step, and then that intermediate product combine with some intermediates to produce the final product. So we have usually more steps to a reaction than just the ones that we see in chemical equations, for example. But some examples where we have here, for example, the radical of oxygen combined with methanol, they are already ionized, so which means they already are ready to react. And in this case, we only have one step of reaction. And in this case, the power law will just be, we will use the coefficients as the power or the order of the reaction with respect to each reactant. But funny enough, most reactions, even when they have multiple steps, they still follow the power law. And we call them that they follow the elementary rate law, which means we can use their stoichiometric coefficients as their powers. Then obviously, as we mentioned, this needs to be confirmed by experimental results, or we should see it from a list. There are some standards that contain all the orders of reactions for different reactions. So we either reference it to literature or standards, or we confirm this through experiments. But generally, when we have a balanced chemical equation, we can use the stoichiometric coefficients to define the power laws. And in this case, we call that this reaction, which is not an elementary reaction, it still follows the elementary rate law. As an example, the same example that we had before with nitrogen monoxide and oxygen, we can say that the rate of disappearance of nitrogen monoxide depends on NO to the power of 2, because we have the coefficient here, and on oxygen to the power of 1, because the coefficient is 1 here. So we can define rates like this based on our balanced equations. But as mentioned, obviously, we have to determine rate laws experimentally. And they are a function of the reactant, the reaction chemistry, or the properties of the materials, the reactants, rather than the reactor type. So, as mentioned in the last lecture, whatever reaction rate we find on any reactor, we can apply for other reactors. The rate constant K, which we saw in the power law, is not a constant. It's a constant with respect to concentration, but with other parameters like temperature, it's not a constant. It actually heavily depends on temperature and other parameters, such as the presence or not of a catalyst, and so on. And the total pressure of the gases in the case of gases, the strength of ions, and choice of solvent in the case of liquid reactions, and so on. And the dependence on the concentration, the dependence of the reaction constant on temperature can be defined through the Arrhenius equation, which you might be familiar with. Basically, we have the reaction constant is exponentially proportional to the temperature. We have A as a pre-exponential factor, and then we have activation energy, which we will look into what it is in a minute. And then we have the gas constant, which is a constant, and then we have the absolute temperature, T, which is in Kelvin, and then when it varies, our rate constant also varies. So the Arrhenius equation is that the equation that defines or determines how our rate constant depends on temperature. Now let's see how this actually looks in real life. So when we have a reaction constant K here and we have the temperature here, we can see that it increases exponentially here. And what this means in practical terms is that the more you heat up a reaction here, the more highly excited the molecules will be, which means they will have a they will gain an energy level that gives them that makes them react faster. So the reaction rate increases when we increase the temperature, because we are exciting the reactants, and we're making the movements inside the reactor faster, or the bouncing of the reactants with each other and so on. So we're in a way increasing this energy level by doing that. And the reason we need this energy level is because we have something called activation energy. And this is the energy barrier that we have to overcome in order for the reaction to take place. So basically, the reactants have to get to a point in through their movements to a potential energy level that actually then can only spontaneously react to become products. So as you can see here, just an illustration of it is basically, it's like pushing up something, a rock, for example, up a hill to the point where it can roll down. And this is the barrier that you have to overcome in the case of chemical reactions. Yeah, and the reason we have activation energy is because obviously we have this reactants, they have to extend, stretch, and break their bonds before they can become products. And in order to get that excitement, or that situation where their bonds are broken and ready to bond to form different bonds, that's the energy barrier or activation energy that we need to overcome. Here is some other illustrations. If we have a coordinate of reactants and products here, for example, and here is the potential energy level. If the potential energy level of the reactants is here, we need to overcome this energy barrier before we can start producing products. And you can see the state of the reactants. They become simple molecules before they can become products. And similarly here, we have a transition in just in the distance of the bond. And the reactants basically have to overcome this barrier before they can become products as well. Yeah. And we can also here see here the dependence on temperature. As temperature increases, the fraction, if we have this kind of Gaussian distribution of probability of reacting fractions, as we increase temperature, the shape looks a bit like this. So it shifts more to the enough energy collision space, and we have basically more of the collision is leading to products. So the fraction of molecules with sufficient energy increases as we increase the temperature of the reacting system. We can do this without increasing the temperature, and the way we do that is basically using catalysts, because catalysts, they provide alternative routes for the reaction. and this alternate route usually has a lower energy barrier, or a different well a different pathway towards products. And if you see it here, it's when we add catalysts, it's as if we make a tunnel here that can just take us to the products. Yeah, so that's why we use catalysts, because they don't really participate in the reaction, but they make in a way that our bonds can break faster, so that we don't have the initial activation energy barrier that we need to overcome. Yeah. Then we have reversible reactions. In the case of reversible reactions, where we have reactions proceeding in the direction of obviously products, but also backwards, then we use thermodynamic relationships that relate the species concentrations at equilibrium. So when forward and reverse reactions are occurring at the same rate, so equilibrium in this case is the rate of forward reaction and the rate of backward reaction are equal. And since they are equal, so basically the products are forming at the same rate as the reactants are forming. And in this case, the effective rate is 0. So the rate of reaction of each species is 0, but not because the reaction stops, it's just because they cancel each other out. So we have an equilibrium where we have backward and forward reactions taking place at the same pace. And when we have such a situation, basically the chemical composition of the system does not change, because, as we said, the reactants in products are forming at the same time. But we can define an equilibrium constant that is defined as the product of the products to the power of their coefficients divided by the concentrations of the reactants to the power of their coefficients. So it's a bit of a power law for equilibrium, if you will. It's called the reaction coefficient, and it's an equilibrium constant. It relates the amount of products and reactants at equilibrium, at the chemical equilibrium. At any other situation than equilibrium, then we have a different situation, because in that case, the rate of a reaction of a species is not effectively 0. So the relationship will still involve the equilibrium constant, but it will not be exactly like this. And just like with irreversible reactions, the equilibrium constant also depends on temperature, and in a much similar way as the Arrhenius equation that we saw. And when we don't have change in the total number of moles and in the heat capacity, then we can define that Kc at a given temperature will be equal to Kc at the previous temperature, and times e to the power of the heat of reaction delta H divided by the gas constant, and then times 1 divided T1 minus 1 over T. So basically, once we have the equilibrium constant at one temperature, we can find what the equilibrium constant will be if we change that temperature. So whether if we increase or if we decrease, then our equilibrium constant will be different, just like our reaction constant in the case of a reversible reaction, an irreversible reaction. So yeah, this is you can consider it as an Arrhenius equation for irreversible reactions. And Kc basically changes with temperature, as we said, and it will increase in the case of endothermic reaction if you don't know, an endothermic reaction is a reaction that it takes heat to take place. So basically it requires heat to proceed, whereas an exothermic reaction is a reaction where basically it releases heat as it proceeds. And therefore the equilibrium constant in the case of endothermic will increase, and in the case of in the case of endothermic will increase, and in the case of exothermic it will decrease. It also makes sense because here we require heat, so when we increase the temperature, the reaction will be faster, so the equilibrium will be reached faster, and our equilibrium constant will be higher. And here the opposite. Let's take as an example now a reversible reaction. We'll try to make a power law for this reaction, and see how that relates actually to the to the thermodynamic relationship that we just saw for reversible reactions. If we have benzene that goes to diphenyl and hydrogen, we have the reaction constants basically for forward and backward with respect to B expressed like this. And you can see that the forward rate of A is the disappearance, so we can define it just we can do the power law, which means it's Kb, the rate constant, to the power times the concentration of this reactant, which is the benzene, to the power of 2. And the reverse will be, in this case, these are the reactants, so the reverse of the reverse rate of B will be K minus B, which is the rate constant backward, times the reactants, in this case D and DH2. And this is the rate of formation of benzene. And in a reversible reaction, we have the formation and this disappearance of the same material could be at different paces at different situations of the equilibrium. If we are at equilibrium, then they are the same, so the rates will effectively be 0. But at any different point, the one could be more than the other. And if we basically combine them and get the net formation of B, formation of benzene, then we have the net rate is equal to the forward plus the reverse. We know the forward is a disappearance, so it's minus, whereas the backward is a formation, so it's plus. And then we can just take out for the reverse side, and then we take out the minus from all. So it means we will have Kb times this in the bracket, so concentration of B squared, which is what we have here, minus Kb times CdHd, which is basically our reverse reaction rate, divided by Kb, which is basically what we took out from here. And this is this is 1 over Kc, 1 over the equilibrium constant. And therefore we can express the rate or the net rate of disappearance of benzene as rate constant of B times concentration of B squared minus concentration of D and H divided by the equilibrium constant. Now what's interesting is basically if you at equilibrium, when we don't have the rate anymore, we can just put this to 0, and if we rearrange this, what we get is exactly what we got from the thermodynamic expression. So Kc will basically be equal to Kb times Cd times CH2 divided by C squared B. So Kc is equal to a reaction constant for that specific species times the ratio between the concentration and their coefficients of the products divided by the concentration of the reactants to the power of their coefficients. Yeah, and that's basically it shows that we can find the equilibrium constant both from power law and the thermodynamic expression. Yeah, so basically, in summary, what we have done now is we have defined a rate of the rate of reaction in terms of power laws. So basically, rate of reaction in terms of concentrations and how these concentrations affect the rate of reaction, which is something that we find experimentally. Then we defined a rate constant that depends on temperature, catalyst, and ionic strength, and choice of solvents, and so on, different parameters, but not on concentration. So we have a relationship that relates rate of reaction with concentrations, which is called the power law. So we have defined that, and the way this rate constant depends on temperature is the Arrhenius equation. And for equilibrium constant, we have, for reversible reactions, we have equilibrium constant based on thermodynamic relationships, and then we have also a dependence of the equilibrium constant on temperature when we have no change in the number of moles and our heat capacity term is not changing.